Yeah.
All right, we are recording.
Good.
We are live.
They have a slow motion video of a foam strike hitting like with a thing like Columbia to see experimentations on what it would do, and it is pretty crazy.
What's hilarious is the engineers were basically saying, nah, there's no way a piece of foam could do that. And then they did the experiment, and they're like, oh my gosh.
Yeah, the engineers will say that, and the physicists will be all like, really? Because it's a thing.
Did you do your sanity check? I want to go. That makes me think of pierogies. Now I want pierogies. Thank you, Mark.
Oh, yeah.
Why are you saying me?
That's a very sarcastic thing. Oh, yeah, but it is my fault, isn't it? Because I'm the one
Oh.
that always smoke.
Thank you, Dr. Harmon.
Yeah, you're welcome.
Now I want pierogies.
Well, now I do too, so thank you for mentioning that, because it hadn't occurred to me to want pierogies. So now that you just said you want pierogies, now I want pierogies.
All
I
right.
don't know what those are.
You've never had a pierogi?
Potato.
They're like
it's like
ravioli.
potato
Ravioli, but
goodness.
with potatoes.
If you put mashed potatoes inside ravioli,
That's a pierogi.
Yeah.
Yes, it's delicious.
It is
Actually,
amazingly
it is.
delicious.
And actually, at first you think, why would I want, but you do.
Zach, when you watch this video, you better have pierogies next to you because you will be wanting
It's
them.
pure carbs and other carbs.
Right? Like, that's how I feel about it. Like, when I see it, I'm like, oh, yeah, that's what that is.
Carbs and carbs and carbs.
But that's the great part
Okay,
about
so
it.
far what we've done is we've said where the maxima and minima are. Now let's get fancier and find out what the actual brightness is as a function of position along the screen. So what's the actual brightness pattern look like?
Then take a derivative?
You could.
You can always take one derivative.
Let's find the intensity as a function of position on the screen. So we'll let the phase difference between the waves from two slits at point P just be some delta. So that if delta was pi radians, you've got destructive interference. If it's 2 pi, 4 pi, etc., you've got constructive interference. But maybe it's 0.3 pi radians or something like that, or 37 degrees, or however you want to express it. So that phase difference between waves from two slits at point P on our screen be delta. We'll use a small Greek letter delta to be that phase difference.
oh, that's big delta.
No, 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 no. Are you crazy, man? Why would you use a big delta for something like that? Yeah, I know. God. The light waves can then
Yeah, I know. God.
Here, I used to think you had such attention in physics, but oh well.
But then you got knocked off the top of a building.
Yeah.
You can build another times.
So, then we can represent the waves by E1, wave from the first slit, is A naught sine omega t. If we choose the time equals 0 properly moment, if we choose time equals 0 properly, the moment properly, you can make it be sine omega t. In general, it'll be sine omega t plus some phase shift. Make the clock start running such that it's equal to 0 at that time, and the electric field's increasing at that time, and then it'll be A naught sine omega t. A naught is the what of the wave? Its amplitude. Yeah, A naught is its amplitude. And E2, well, if their slits being illuminated by the same source, then they'll have the same amplitude for the wave that's coming out of them. E2 will be A naught, same amplitude, sine of omega t plus delta because of that phase shift between the waves arriving at P from the two slits. So these are the light waves at point P, not at the slits, but at point P. They're in phase at the slits themselves, but the light waves, I'll make that clear here, at P can then be represented like this. Now, strictly speaking, the amplitudes won't be the same at point P because one of them is slightly further away than the other one is. However, that will be a very tiny effect. If the slits are 1 millimeter apart and the screen is 10 meters away, and furthermore, right, if it's the first bright spot, the path length difference between them is 1 wavelength, right? 1 wavelength out of 10 meters, not a big deal. So we're ignoring the fact that the amplitudes are slightly different because of the fact that the slit differences are slightly different. But what you can't ignore is the phase shift between them, because that's what's leading to the destructive and constructive interference in the first place. So you can't ignore that. So we'll assume equal amplitudes, but we'll throw in the phase shift. All right. So the total electric field is then E equals E1 plus E2. Electric field from slit 1 plus electric field from slit 2 is, watch this amazing algebra right here, A naught sine omega t plus A naught sine omega t plus delta. So if you're wondering how I came in, never mind.
It's like magic.
Yeah, how did I do that? See, what I did is, okay.
Wait, I see how you did it. That's
Yeah.
not magic.
No, you're right, it's just math. Which to most people is magic, but
Yeah, seriously.
yeah.
Most people it's equally unfathomable.
Yeah, it's beyond that. I don't get distracted there.
Now we use the trig identity that says,
This sounds like that.
this does, yes, sine alpha plus sine beta is equal to sine beta plus sine alpha. No, that's not the trig.
It's like, that's a really crappy trig identity.
Yeah, that's the worst one ever. Yeah.
It has been empirically determined to be the most useless thing you can
Right.
say about trig
Go
identity.
into the Wikipedia page and trig identities and add that. No, don't.
Do it.
No,
Do it.
that's vandalism.
You will have your physics
2
license
cosine
revoked.
half of alpha minus beta sine of half of alpha plus beta.
Get our physics license revoked.
What's that?
Get your physics license revoked if you
You
did
would
that.
get your physics license revoked for that.
Is that half like inside?
It's, yeah, so it's this. I don't want to keep writing those square brackets, but yeah, that's what I mean by it. So basically everything following a trig function that isn't the start of another trig function is the argument of the trig function. Right?
Unless it's a trig function within a trig function.
Yes, then it's very good. Then you're getting tricky with it.
Now it's becoming more like Inception.
Yes, what's
That was really exciting like that.
Getting tricky with it. That's right. I am that cool in 1990. Let's see.
Will Smith.
Will Smith.
That's right. Yes.
Will Smith was pretty cool, man.
He's still cool today. With alpha equals omega t, and beta is omega t plus delta, since after all that's the two signs we're adding up there, then E is equal to, yes, stop it, 2a naught cosine of minus half delta times sine of omega t plus is here I've got half of alpha minus beta. So alpha minus beta is going to be minus delta, and I multiply by half to get minus 1/2 delta for the cosine argument there. Okay. Like going like that. So I said, I'm adding these two guys, right? So it's omega t and omega t plus delta. So I let alpha be omega t, beta be omega t plus delta. So here I want half of alpha minus beta.
Okay.
Yeah, that's what I'm doing there. And then over here, half of alpha plus beta gives you half of 2 omega t plus delta. Or in other words, omega t plus half delta. And then there's overall 2 out front, because there's an overall 2 out front. Profounder words were ne'er spoken. That's almost as profound as sine alpha plus sine beta is equal to sine beta plus sine alpha.
Although they
Or,
do teach that theorem in what, 7th grade? A plus B equals B plus A.
yeah, right. Or E is
This seems to be common sense.
2a naught cosine
It is
of half
common sense.
delta, because after all, cosine of minus theta is equal to cosine of theta. 2a naught cosine of half delta multiplied by sine of omega t plus half delta. And so our conclusione is, that's Italian for conclusion. No, it isn't. I mean, maybe it is. It's not conclusione.
Funny story about.
Conclusione, yes.
Like
Sorry about
Megatone.
Oh, yeah? Really? Oh, yeah?
It's all on the break.
Okay. So what have we learned on the show tonight, Craig? That, you guys watch Craig first. All right, anyway, phase of the resultant wave is halfway between the phases of the two waves, right? In other words, the resultant wave has a phase angle of half delta, halfway between 0 and delta. And the amplitude is 2a naught cosine of half delta. Phase of resultant wave is halfway between the phases of the two waves. And amplitude of resultant wave is A naught prime is equal to 2a naught cosine of half delta.
Box.
Special cases to come when I am satisfied that pencils are no longer moving. Yeah, there you go, right. Now, pencil's still moving.
I don't know any cool pen tricks or that.
Now,
You're doing a little dance.
I can do this.
Hey.
I can juggle one egg. It's remarkable.
I can balance an egg on its end, only on the equinoxes.
Only on the equinox. Oh, I can raise you.
Oh.
I can balance them on the solstices.
You ready, Zach?
I can juggle 4 classes.
All right, very good. Excellent. Special
One day I
cases.
find something else to do.
What if delta is 0, or plus or minus 2 pi, or plus or minus 4 pi, et cetera, et cetera, et cetera? Well, that would say that A naught prime was equal to A naught. Because in that case, you're going to get cosine of 0 or pi, or 2 pi, and so on and so forth. And actually, I should say here, really we ought to be saying it's the absolute value of this, because if the amplitude works out negative, that doesn't really matter, because all you really care about is how much it goes back and forth. So let me add that. The amplitude is the absolute value of 2 a naught cosine half delta. So in a case where you get 0, plus minus 2 pi, plus minus 4 pi, etc., the amplitude becomes twice the amplitude from either slit alone. And if the phase difference between them is 0, or plus or minus 2 pi radians, or plus or minus 4 pi radians, how many wavelengths is the path length difference if the phase is some integer multiple of 2 pi? So if there's one wavelength of path difference between them, what's the value of delta? How much are they out of phase? Be 2 pi, right? One wavelength is 2 pi radians of phase.
Yeah.
2 wavelengths is 4 pi radians of phase. 3 wavelengths is 6 pi radians of phase. So in other words, delta equals some integer multiple of 2 pi is the case of total constructive interference. The waves are in phase with one another. Not surprisingly, that means the amplitudes fully add together, and the amplitude ought to be twice the amplitude of either slit alone. That's the point there. So this is total constructive interference.
Yay.
Yes. TCI. That's right. Total constructive interference. On the other hand, why, what if delta is, say, plus or minus pi, plus or minus 3 pi, plus or minus 5 pi?
We're in the third hour, right? No, wait.
No.
Oh my God, it's the second hour.
No, I think that was like, well, it's south.
Yeah, so it's southern incarnate or something. Yeah. Why, what will A naught prime be if we get plus minus pi, plus
I
minus 3
reckon
pi?
it-
Apple pie.
It'll be 0. Yes, A naught prime, it will be 0.
What about the apple pie?
There ain't gonna be no apple pie in this room, so.
I love you,
Yeah.
Yeah.
Let's go.
Y'all already had my delicious cookies. There's oatmeal raisins, so don't be thinking you're gonna get apple pie too.
Aw.
Total destructive interference.
But they in Lieutenant Dan invested in some sort of fruit company.
What happened to your legs, Lieutenant Dan? It's y'all can't tell. It's like nothing.
There's a reason why it won, what, Emmy Award for Best Picture?
That is the picture. Great film.
The intensity, which we'll call I, is proportional to amplitude squared. There's the proportion fish. It's proportional to amplitude squared.
What if it was right here?
We will. So I is a constant times A naught prime squared. See, I just did.
Boom!
Yes. So that'll be constant times 2A naught squared multiplied by the cosine squared, 1/2 delta. Plugging in my earlier A naught prime is 2A naught cosine half delta. So if I square that, I'm going to get constant 2a naught quantity squared cosine squared of half delta. Last time I checked, 2 squared is 4.
What?
It's in 10%. So we get 4.
For sufficiently large values of 2.
Yes. Yes, 2 is equal to 1 for sufficiently small values of 2. The astronomer's rule.
I thought it was 2 times log base 5 of 2 over log base 5 of 2.
It is that as well, yes. And sine half beta is equal to sine half beta. Other news. Or I equals 4i naught cosine squared of 1/2 delta. That's where we throw the box around, where I naught is the intensity due to a single slit, because the intensity is proportional to a squared. So it's constant times amplitude squared. Well, for a single slit, the amplitude was a naught, so constant a naught squared is the intensity for a single slit. So I naught equals intensity due to a single slit. But in
Thunder mark?
fact, delta is equal to 2 pi over lambda times d sine theta, because d sine theta is what? No, it's not, because we're not necessarily at a point of
It's
construct
the
that we're totally.
path lengths difference.
Path length difference, yeah. D sine theta is the path length difference, right? And so, path length difference, d sine theta over lambda, is the fraction of a wavelength that the path length difference is, right? Path length difference as a fraction of a wavelength. And because surely I'm going to be glad I did this, henceforth path length difference is PLD. So I'm tired of writing path length difference. Path length difference as a fraction of a wavelength.
Forever and ever.
Yes. And there's 2 pi radians of phase in one wavelength. So in other words, 2 pi radians times d sine theta over lambda, the fraction of a wavelength that we are out of phase, is the number of radians of phase difference between the 2 waves. So delta is 2 pi over lambda times d sine theta. Happiness and joy cometh therefrom,
Only in Scotland.
only in Scotland.
Okay, Nathan.
National animal's unicorn. Oh no, Sweden or whatever.
It's like the blue angels flying over my head sometimes.
So far, this isn't a PDB reference.
No. We have not Ubered yet.
Yeah, I said that. Okay.
But 2 pi over lambda d sine theta is going to be approximately 2 pi over lambda times d over L times y. From our earlier considerations that sine theta is approximately just y over L. So, as a function of y on the screen, where y is distance on the screen away from the center of the interference pattern, I as a function of y is going to be 4i naught times cosine squared pi over lambda times, why do I have a pi there? Oh, because it's half delta, yeah. Pi over lambda times d over L times y. Boxeroni. Which of course is not the Italian word for box.
All that stuff after cosine.
Yeah, yeah, yeah.
On my own strip, we're good.
That's exciting.
No, not really.
All that's the argument of the cosine squared.
And can we use the obtaining value for I naught?
Do what?
Value for I naught?
Well, you could by, so the problem is, it kind of says with I as the intensity due to a single slit. The problem is if you just have a single slit there, you just get this diffraction pattern that's kind of spread out on the screen. So what this I naught is really kind of the thing that that is a base that we're multiplying by, so to speak here. But really, in other words, if you have two slits, then I naught is 1/4 the brightness of all the maximum. If you have three slits, I naught is 1/9 the brightness of all the maximum. But I naught is going to be set by how bright is the laser or whatever light source you're using to illuminate the slits in the first place. It's going to be set by that. So the most important thing is that this is telling us that the functional dependence is cosine squared of all this stuff times y. In other words, if I were to make a plot of brightness on the screen as a function of y, so here's I as a function of y, then if I mark off the locations of the maxima, which are L over D times lambda, 2L over D times lambda, so remember last time we showed that along the screen, successive maxima are separated by a distance L lambda over D. So if y equals 0 is the center of the pattern, there's a primary maximum there. It's two slits, there's just a maximum there because all the maxima are primary maximum. There's only one kind of maximum. 3 L over D lambda, 4 L over D lambda, and then minus on the other side, minus L over D lambda, minus 2L over D lambda, this is so much fun, minus 3L over D lambda, oh gosh, I just feel obliged to make it the same width on both sides, minus 4L over D lambda from it's symmetric, that's right, yes. Then, here's its amplitude, which we just call that 4I naught. And so, it's going to be a cosine squared function. So what's the maximum value of cosine squared? What's the minimum value of cosine squared?
0.
0. No, that's cosine, right? Cosine squared, right? Yeah. So it looks like this. It's a cosine squared thing. So it's something like.
It actually makes that sound.
Yeah. And this is a crappy plot, but you know what it's supposed to look like. It's supposed to be beautifully symmetric cosine squared plot. Yes. We'll add that in post-production.
But if you take the integral of it between negative infinity to infinity, you get 0.
Actually, you don't.
Oh.
There's an infinite area under that curve.
Oh yeah, that's
It
right.
doesn't go negative.
Because it's not not, it's an even function.
But thank you for playing. We have some lovely consolation prizes for you, including rice-a-roni.
Does rice-a-roni come in a box-a-roni?
But it is the San Francisco treat. Dr. Tree still likes to eat rice-a-roni. We were talking the other day about back in this, no, he eats it. He really does. Back in the 70s, on game shows, the consolation prizes were always included rice-a-roni, basically. And they used to have these commercials. I'm sure they're on YouTube.
That's because they're major sponsors.
Yeah, rice-a-roni. The flavor can't be beat. Rice-a-roni. The San Francisco treat. And they have like a San Francisco cable car going along. So, yeah.
Why San Francisco?
I guess
Whole house.
because it's Rice-A-Roni Incorporated, San Francisco, California or something.
It's rice-a-roni comes in a box-a-roni.
It does indeed Roni, yes. That's a good point, Roni.
Very ironic.
Yeah, it's ironic, as a matter of fact.
Actually, at Thompson's store, you can buy like these rice-a-roni things that come in a bowl, and you can fill it with water. You throw it in the microwave, and you have instant rice in like a minute.
Yeah, dude, it's called minute rice. It's been around for a long ass time.
But it's rice-a-roni.
Yeah, I don't think that's special. In any way.
It is for Dr. Drews.
All right, Josh will like this. But Nathan will like it even better. Phasers. So I'm being ironic when I say Josh will like this. Because
Yeah, I
this
was
is
going to say,
to-
because I don't like Star Trek.
So I was
called.
I was
Josh
making-
doesn't know anything about Star
No, this
Trek.
was one of those, Josh is gonna like this, but Nathan's gonna like this. Yeah, so, we're gonna use phasers, it's gonna be stunning. Oh,
Wow,
it's really
that was
killer.
really bad. Even I got that one.
Yeah.
Set phasers to stun.
I said
No.
find the kill.
So, we just did it, we just added two waves together, two harmonic waves together, using a trig identity. We're gonna show how to do it graphically, which we can cast it in terms of phasers in the complex plane, although in my notes I don't, but I'll mention that we can also cast this in terms of phasers in the complex plane. So here's the deal. Remember that complex plane has a real axis and an imaginary axis. In my notes, it's just an x-axis and a y-axis, because it doesn't really have to be complex phasers, but I think it is better to think of them that way, probably. And if we have e to the I theta, tell me, how can I rewrite e to the I theta?
Cosine theta plus I sine.
Glorious! Yes, it is in fact cos theta plus I sine theta. So, what if I have a naught e to the I omega t? What can that be written as?
A not to the
A naught cosine
cosine of omega t
omega t, a naught cosine omega t, plus,
well, I was just going to put the a naught as giant brackets,
you
but
could, plus I times,
sine omega t.
times also still, because I didn't factor the a naught out, basically.
Yeah.
So I'm just going to throw it and go through. Plus I, a naught, sine omega t. And if I had a naught e to the I, let's say, omega t plus delta, why, that would be a naught cosine of omega t plus delta plus I a naught sine of omega t plus delta. Now there's a tendency when representing when representing trigonometric waveforms with complex waveforms to say, but the actual signal won't make that the real part of the complex number. We're going to make it the imaginary part. There's nothing stopping us from doing that. We could make it the real part, we could make it the imaginary part, but I've been writing my waves as sine omega t's, or sine omega t's plus delta. And if I want to have things that are sine omega t type thingies, I take the imaginary part of the complex phasor. And so that's what we're going to do here, which is kind of good because it emphasizes that both the real and the imaginary parts of a complex number are real numbers, right? And so I think it's actually good to, for once, use the imaginary part. Our conventional we always take the imaginary part to get the physical disturbance. What's that?
We always see the real parts of conventional.
That, usually people take the real part, but it's perfectly fine to take the imaginary part. Imaginary part is just as real as the real part. is. The imaginary part of a complex number is a real number. And for that matter, imaginary numbers actually exist. They're not like figments. So we're going to take the imaginary part every time for these purposes here. It's going to be great.
Trying to
So-
explain that to to an algebra 2 person is kind of hard though.
Yeah, well,
Yeah, right. Like this.
Like, why are we learning imaginary numbers when they're only imaginary?
yeah, I know it's a really unfortunate designation.
Yeah, misnomer.
Yeah, there's this article in this math magazine that back when my PhD was about that, and some guy wanted to rename it J.
Yeah. Well, electrical engineers tend to use J.
Yeah, that's what it's like.
Yeah. Because I means current.
Or just don't call it an imaginary number.
Complex
You can call it a complex.
As we mentioned before, you can represent the complex number, so this arrow in the complex plane, which I probably shouldn't draw an arrow to, this arrow represents a naught e to the I omega t if it's understood that this arrow is rotating around the axis with, around the origin with angular frequency omega. And then at all times, its projection onto the real axis is a naught cosine omega t, its projection onto the imaginary axis is a naught sine omega t. So this rotating phasor can be thought of as representing this wave that we're trying to consider.
I've used this for something else before.
We were doing it some in physics 280, I think, probably, something like that. Yeah, yeah, this isn't the first time this has ever graced your consciousness. And here's another good example of it, basically. So, this phasor represents E1, which we said was going to be A naught sine omega t. The imaginary part of it is A naught sine omega t. So the phasor is representing that wave. It's got both a real and an imaginary part, and we're only going to, in the end, want the imaginary part.
Isn't that what we're saying? That E1 is even the imaginary part?
E1 is the imaginary part of that phasor, yes. Right. So in fact, yeah, if we want to get all fancy, we can say M of A naught e to the I omega t is E1. Imaginary part of A naught e to the I omega t is E1. And if we want to represent E2, we just shift by angle delta. So in other words, there's phasor A naught e to the I omega t, and we're drawing this at some particular snapshot in time. So some particular value of t, and then as time progresses, everything rotates around the axis counterclockwise at angular frequency omega. So if that's A naught e to the I omega t, then if I just add delta to the angle, the resulting phasor is the shifted A naught e to the I omega t plus delta. And note that they could also have different amplitudes. There's no reason that they have to have the same amplitude. Just usually to have the same amplitude because that's what we considered before.
Could we modify this to
could, yeah. But typically, we're not gonna worry about such a thing, but you certainly could. And since complex numbers have the property that the imaginary part of z1 plus z2 is equal to the imaginary part of, what am I going to write here? The imaginary part of the sum of two complex numbers is simply the, no, we don't need no stinking complex conjugates here. Z's are complex numbers. Yeah, so just Z's are complex numbers. The imaginary part of z1 plus z2 is, I'll put it the way I do in my notes because it's in the end equivalent. What's true? The y component, because you know this is the y component of a vector, if you like. The y component of the sum of two vectors is simply the, oh, you're thinking too hard here. The y component of the sum is the
Sum?
sum of the,
Components?
yes, the y
So the y
component of the
components of the
sum is
individual?
the sum of the y components, right? If I add two vectors, the y component of the sum of the two vectors is the sum of the y components, right? In other words, for vectors, we would say the y component of the vector a plus b is ay plus by, right?
Yeah, that.
Oh, so you're
Right?
gonna say it's imaginary z1 plus imaginary z2.
Imaginary of z1 plus imaginary part of z2. Yeah. M of z1 plus z2 is M of z1 plus M of z2, right? So now suppose that I'm adding two phasors, and let me drop the idea that they have to have the same amplitude. They certainly don't, but I will have them have the same frequency. We're not really interested in adding phasors at different frequencies, because then they just go crazy out of phase with one another. We want to add phasors that are in phase, because we're talking about interference, and you only get interference from ways that are in phase. Or at least, well, they maintain their phase relationship with one another. They stay the same amount in or out of phase at all times. That's when you get interference between two waves. So I can get interference between the waves coming from two slits only if they're both being excited by the same source. If they're being excited by two different flashlights, I won't get interference because there's no particular relationship between the phase of one wave and the phase of the other wave, but they're just illuminated by two flashlights that are emitting waves at random phases. So the imaginary part of a1 e to the I omega t plus a2 e to the I omega t plus delta is, of course, the imaginary part of a1 e to the I omega t plus the imaginary part of a2 e to the I omega t plus delta. But the reason this is happy for us is, in other words, the imaginary part of a1 e to the I omega t is a1 sine omega t, and similarly for the other piece, the imaginary part of a2 e to the I omega t plus delta is a2 sine of omega t plus delta. But we're going to see that then that's wonderful, because all we have to do is add these two phasors together like they were vectors and find its y component, find its imaginary component. And you'll see what I mean when I do it, basically. You'll see why this is useful when I actually do it. So, any questions? In other words, what we're trying to do is say, what happens if I add these two guys together? Well, I could do it with fancy trig identities, or I could draw the phasors that represent them, add them together, take the y component, the imaginary component, and that will be the result. And again, you'll see what I mean when I do it.
Oh, okay, well, then what then is the intensity of the line?
find is that the result, we can find, what the point is we'll be able to easily find the amplitude of the resultant. And that squared will be proportional to the brightness of the spots on the
It's
screen.
like the fancy trig identity is almost a little easier to do.
No, it's not. Trust me on this. Trust me on this. Because this is going to let us, for example, figure out, what if I have 15 slits? Have fun using trig identities on 15 slits. We're going to show this really cute thing that you can do. So this is going to be great. Trust me on this. Come on, believe in me, Mark. Come on. I want your faith.
God Harmon,
Can't
the
say
God
that.
of the big.
So let's do an example. Use phasor addition to verify that what we saw above was true, that A naught sine omega t plus A naught sine of omega t plus delta is equal to 2A naught cosine half delta times sine of omega t plus delta. Draw the picture, and then we will talk about it. So before we were drawing, what I'm going to do is, the phasors add like vectors, so I'm going to do a tip-to-tail vector addition drawing. So I'm going to call, I've drawn A naught at some arbitrary angle with the real axis and call that alpha. Now, it would be fine to think of that as being omega t. That is what it would represent, really. Because remember that the phasors rotate around, and if one of them is just supposed to be A naught e to the I omega t, then omega t is the angle at any given time that it makes with the real axis. But I've just labeled it alpha there. So here's a phasor of length A naught, here's another phasor of length A naught, and the angle between them is delta. Now before, I drew them both at the origin with an angle between them of delta, but remember that when you add vectors, you can either do the parallelogram rule, or you can add them tip to tail, and I'm doing them tip to tail addition. So I've just translated this guy over parallel to itself and drawn it at an angle delta from the line that's the extension of the first phasor there.
Is that angle alpha, is that omega t?
That's omega t if you like, yeah. You can make that, you can consider that to be omega t if you like. It is, really, at any given time, that would be omega t. Okay. Now, if this angle's delta right here, what is this angle right here?
180 minus delta.
180 minus delta, or pi minus delta if we stick to radians. And this triangle is, what do you call it? 2 sides are the same. Isosceles?
Isosceles.
I said this triangle is isosceles, right? Because these two vectors are the same length. So this is an isosceles triangle. The angles in a triangle add up to
180.
180 or
Pi.
radians pi. They add up to pi. So these two angles are equal, and when you add them to pi minus delta, you have to get pi, so each of them has to be delta over 2. That's how I know these two angles are both delta over 2, because delta over 2. They're equal, so they both have to be the same. Delta over 2 plus delta over 2 plus pi minus delta is pi. So therefore, those angles are both delta over 2. So, from our diagram, we know that A prime, the length of the resulting phasor, is equal to 2A naught cosine of 1/2 delta. Because all you have to do is drop a perpendicular and make a right triangle, make two right triangles. And the hypotenuse of the right triangle is A naught. And so therefore, and then there's this angle 1/2 delta, so therefore this length, half of A prime, is A naught cosine 1/2 delta. So A prime is twice A naught cosine of 1/2 delta. So without the fixed fancy trig identity from this diagram, we got that the amplitude of the resulting phasor is in fact, the length of the phasor is in fact 2A naught cosine 1/2 delta. Ooh, that's beautiful. And furthermore, the angle for the resultant is, actually I don't know why I didn't just call that omega t. I'm looking at my notes and thinking, why didn't you just call that omega t from the beginning? So,
Yeah, cool.
yeah,
I pity the fool.
yeah, I pity the me. Yeah.
That was 2 days ago, Mike.
The angle for the resultant, notice that it's 1/2 delta ahead of omega t there. So the angle for the resultant is omega t plus 1/2 delta. That's what it's supposed to be. Omega t plus 1/2 delta. You guys didn't stop me there. Plus delta over 2 is supposed to be right.
I have faith.
You had faith. Stupid. I have it wrong in my notes. I need to fix that. Don't be so foolish. No, do be so foolish as to have faith. So indeed we get 2A naught cosine of 1/2 delta. Well, what do I want to say here? I'll break it into two pieces. If I take the y component, I get, what do I want to say here, but. So resulting phasor is 2A naught cosine 1/2 delta for its amplitude, and then it's e to the I omega t plus 1/2 delta, because the angle away from the real axis is the argument of the complex exponential for the phasor. Right? In e to the I theta, theta is the angle away from the real axis. So the phasor is 2A naught cosine 1/2 delta, e to the I omega t plus 1/2 delta. And so m of that is what? The last thing before we take a break, m of that is, the imaginary part of that complex phasor is?
Is what is the sine omega t plus 1/2 delta?
Yeah, I just take the sine here, because the imaginary part of e to the I theta is sine theta. So I take the imaginary part of the exponential, that's just sine of omega t plus 1/2 delta, and I still have to multiply by that overall amplitude, the length of the phasor, the magnitude of the complex number. So it's 2A naught cosine 1/2 delta, sine of omega t plus 1/2 delta, which is what I was trying to show. No, so in other words,
Okay.
so I've done what I wanted, because this thing on the left-hand side is the imaginary part of Z1 plus the imaginary part of Z2. And this beast is the imaginary part of Z1 plus Z2. And so therefore, we have shown that A naught sine omega t plus A naught sine omega t plus delta is 2A naught cosine f delta sine omega t plus f delta. Done what we wanted. Glorious.